Okay, let's get the webcam a bit better positions. Good afternoon, here's Harry, and welcome to Practising Programming in C, where we're going to continue to learn about threading. Last week on Practising Programming in C, we kind of made a start on learning about threading. So here's what we got going. Here's our simple program. All it does is it initializes a couple of threads. We've got thread A here and thread B. Thread A has a bunch of additional stuff kind of done to it. So we actually initialize its a set of attributes, and we make a change to one of the attributes, and I think we also here we just get the affinity here of this one, and for each thread we create it, and we also destroy their attributes, and then after we've created them we join them. And for each of these create things, we obviously need to pass the thread itself. We pass the attributes where we can actually pass null, and it would set the defaults. We pass the function that it would call. So in this case, it would do thread A stuff, and then we pass the arguments that thread A stuff would need to work on. So we're using all of the parameters, where we could actually just go null for that, and we could also do null here as well actually. But I think the function will actually still work though, to be honest with you. Just double check. Yeah, it's only if args it goes and does some stuff. So probably what we'll see here, I'm just going to run it. Probably what we'll see is that thread B operates, but thread A doesn't. So yeah, you see thread B's stuff comes through. Yeah, but I'll just leave them back in, and then we can see that thread A and thread B both do some work. And you can see also, I'll just describe a little bit of what it's doing. So the data is, it's just, you can see they're just printing out like a number. It's printing out the function name, then a number. Well, all it's doing is, it's starting out at this number here, and it's supposed to go for this number of iterations. So for A, we've got it starts at 8, and it's supposed to do 12 iterations. For B, it starts at 4, it's supposed to do for 4 iterations. But you can see here that thread A occurs once, twice, 3, 4, 5 times. It doesn't occur 12 times, and that's because we've told it that it can't be attached to, basically. So even we can't be joined to. So even though we are calling this join thing, it's actually not allowing the thread to complete its work before we continue past that call, basically. But if I was to do this, then we should see that it can continue on, and we should see just a few of A itself. Yeah, and we do. So that's basically where we were at, and that was quite quick to do actually. In the previous stream, it only took about 20 minutes or something to actually, 20 minutes into the stream, this was where we were at, and then we were just sort of looking through the attributes. We were learning more about the attributes, looking at the man pages for those, and we got through quite a bit. So I'm going to try and just recap what we did. See if I can remember what we discovered. according to the ticks here. So some of these are ticked off because we ticked them off during the stream, and some of them are ticked off because I off stream read about them and learned about them. I think possibly the scope and the shed policy and the shed param. Those might have been things that I'd read off stream, unless it was also a set stack and set stack address, set stack size. But I feel like I did them on stream because they were quite short things to read about. But yeah, so I'll just go through the ones that are ticked. So the set detached state, we've already kind of touched on that. That is this thing here. So detached just means you can't join it, and the other option is joinable, which I already kind of showed, didn't I? So that means it can be joined. Set guard size. Is this a thing that we can't have in Linux? There's one of the things that Linux only supports one type of thing. Let's have a look. So it's to do with the stack, isn't it? It's just adding guard area around the memory allocated for the stack, I think. So it's not too interesting, that. Set the inherit shed. So this is saying whether the thread that we create inherits the schedule parameters of its parent thread, I believe. Either inherit or explicit. Is this the one that can only be? No, this is yeah. We could do both in Linux as well. Yeah. So yeah, it's just exactly what I was just saying. Created using the thread attributes object will inherit its scheduling attributes from the calling thread, or whether it will take them from attribute. So that's pretty straightforward. And then the shed param. So I think these things are kind of all linked, or these two at least, the shed policy and the shed param. And I think I looked these up, I think I read these offline. Now, from memory, the shed policy, we have a choice between, you've got like non-real-time schedulers and you've got real-time schedulers. And of the non-real-time schedulers, you've got first in, first out, and oh no, I beg your pardon. No, that's first in, first out is a real-time one. Of the non-real-time ones, we've got other, I think is what it's called, other batch, and I think is sporadic one of the ones in there as well. But basically, all that's to do with. Let me just double check that I'm talking about the right thing, actually. Yeah. So shed other, shed batch, and shed idle is the other one. Okay, so that's what I'd forgotten. So basically, shed other, what that means is it's based on the niceness of the process. So if we just look in H top here, this column here is for the niceness of the process. This one here. So you can sort of see that some of these processes are very nice. They've got high niceness value, 19. I think it might be the top whack actually. So for whatever K huge page D is, it's a very nice application. Xorg is also nice, interestingly. UBauth is nice. I'm surprised that OBS is so nice actually. Although that's just that process. There are other processes in OBS that are a niceness of 10. QDRAC control is a niceness of 5, which is kind of understandable. And then you'll see that like the root applications here, the applications that are owned by root, these like system processes, they're going to be less nice until you get right down to the bottom. These are very like unnice applications. And all niceness is, it's simply an indication to the scheduler as to how highly it should prioritize the application. I think maybe if we look at the, yeah, you can sort of see that happening here actually. So there's also this other column, pri, that probably means priority. Now it's not an exact science because you can sort of see that -51 is the priority of this application here, with a niceness of 0, but the one right below it has got a niceness of 0 and a pri of 20, so it's not an exact correlation. But basically, if it's a lower number, if the niceness is a lower number, then the scheduler is supposed to prioritize it higher than a application with a higher niceness value. Basically, it's almost like saying that if a program is more nice, it will sort of defer to other programs, or it will allow resources to be used for other programs. So basically, if you're using the shed other setting, it's going to be basing the scheduling policy on the niceness of the thread, which you can set. Shed batch is basically when it says for batch style execution processes, and it's essentially like, it's a way you use that to say that the expectation is that you're going to be setting up a bunch of stuff to be done, and all of this stuff is supposed to be done kind of together. And all it does in terms of the scheduler, it basically it sort of increases the niceness of the thread without actually increasing the niceness value. So it treats it as if it's like a low priority. It indicates to the scheduler that it should treat it as a lower priority. So if you've got like two threads with the same niceness value, one of them uses shed other and one of them uses shed batch. The one with shed batch should have a slightly lower priority than the shed other one. That's basically all it is. And then shed idle is just said for running very low priority background jobs. So I don't know how that ties into niceness, but there we have it. So yeah, here we go. Currently, Linux supports the following normal non-real-time scheduling policies values that may be specified in policy. Yes, that might have been the thing that I was remembering about Linux supporting something and not others. Now this might be in the sort of the stock kernel, but I believe there are real-time kernels as well that you can actually use. And when you've got one of those, you've got these options for real-time policies. So shed FIFO and shed round robin. So I'll just briefly say what these guys are after having learnt about them. So shed FIFO and shed FIFO first of all stands for first in first out, and basically it's just like a pipe or something. So you kick a job on, and you kick on a bunch of jobs. Let's say that you kick 8 jobs on. The idea with FIFO is that it just takes them off the queue, one after the other, in the order that they're pushed on, basically. So you can imagine like a train going through a tunnel. The train's going in, it's got carriage 1, 2, 3, 4, 5, all the way back. Carriage 1 goes into the tunnel first, carriage 2 goes into the tunnel second, and so on. And then on the other end of the tunnel, you're going to see carriage 1 come out first, then followed by carriage 2, and then carriage 3, and so on. So they're going out in the order that they went in. And it's as simple as that, basically. Round robin is kind of similar, but it introduces the notion of time. And I think they call it time quanta. And the basic idea behind this is that it will try and give each job a fair crack at the whip, basically. So say like you've got a bunch of jobs and they're each kind of like different size. So they're going to need like different amounts of work done on them. Let's just say that job 1 requires like 300 milliseconds of work to be done on it. Job 2 requires 50 milliseconds of work. And job 3 requires 20 milliseconds of work. You should be able to set, and I think that's probably in the shed param. You should be able to set the amount of time that you actually give each go round. But wherever you do set it, so the first one, you've got these job 1. Sorry, it said 300 milliseconds inside. Job 2 was, what did I say, was it 50 milliseconds? And job 3 was 25 milliseconds. If you say that each job, or each time a job is worked on, 100 milliseconds is kind of spent on that job, then what you see happening in the round robin scheduling scheme is that job 1 will come in and 100 milliseconds of work will be done on it. There'll still be 200 milliseconds left to do on it. So you've done like 300 milliseconds take away 100 milliseconds equals, there's still 200 milliseconds to be done on it. At that point, I think what happens is it just pauses it just kind of like saves the state of where that job is up to, I assume, so that it can resume like later on, while it works on job 2. So job 2 only takes 50 milliseconds, so this is going to come in, and I think it's just going to just complete. So we take it, but you can't really take away. I don't think you can take away 100 milliseconds. So this is just like complete, and then I think it's going to go on to the job 3. So this is going to do basically the same thing, really. So it'll be like this, and then you'll have job 1 coming around again, and this time you've got 200 milliseconds, and it does 100 milliseconds worth of work on it, and it's still got 100 milliseconds worth of work to do on it. But I think because jobs 2 and 3 have already been completed, I suspect that at this point it then just goes ahead and just picks job 1 again. And it's finally complete. So that's basically the idea of round robin. Yeah, it just gives the same amount of time. It spends the same amount of time on differently sized jobs to try and make sure it basically prevents like a huge job from occupying all of the resources, preventing other jobs from being worked on. And I think that was it, wasn't it, from the scheduler? Went through other batch, idle, FIFO and RR. Yeah, so we've gone through all of those. So one that we didn't look at, or we didn't go through, is shed param. I want to see where that sporadic thing is, because that's something that is stuck in my memory, but I can't remember what it is. No, it wasn't there. Just bear with me just a sec while I go through these little things. Hang on, was that to affinity actually? It wouldn't have been detached state. It wouldn't have been guard size. Inherit schedule, it wouldn't have been that either. Set scope. No, again, it wouldn't be that either. Is this the Linux only thing? I think this is the thing that's only on Linux. Where does it say that? Let me just try and find that. Yeah, so Linux supports pthread scope system, but not pthread scope process. Yeah, I'm not seeing this, am I? Sporadic. Yeah, sorry about this. I am kind of keen to see if I can find this. Here we go, sporadic task. So, it has a sequence of jobs. Where was this? This was in shed. Can I find that in here? No. Well, I certainly didn't read all the way down to here. Oh, shed deadline. Hang on. That could be what I should be looking for. Nope. Well, there's shed deadline. Yeah, let me just remind myself of what this is about. It provides a deadline scheduling policy for sporadic tasks. This policy is currently implemented using GDF in conjunction with CBS to set and fetch policy. A sporadic task is one that has a sequence of jobs where each job is activated at most once per period. Each job also has a relative deadline before which it should be finished execution. And a computation time, which is oh right, yeah. So yeah, this has the idea of deadlines, doesn't it? So it's supposed to finish. I think the idea is that you're supposed to be able to tell it this needs to finish within X number of milliseconds, and then it just sporadically tries to just get through the jobs, ensuring that, you know, as many people as possible can meet their deadline, I think is what the idea behind this is. So yeah, okay, so that's kind of, I'm glad I've reacquainted myself with that. Yeah. Let's just look at shed param. Remind ourselves of what this was about. It sets a scheduling parameter attribute to the thread to be subject. And it's just one thing, it's just a scheduling priority. So I think this is basically like the niceness, really. I think. Oh, hang on. It's probably actually this, isn't it? 39, 25. I suppose we could try it, can't we? So you're supposed to use pthread attributes, set shed param. So you set atch, and you set the param itself. So the shed param is just the shed parameter. Let's try this on A. And we're going to need, what was it we need? It's a shed param. Okay. Yeah. And the only thing that a shed param contained was shed priority. Okay. So what I'm going to do here is I'm going to just I don't want to read my file. What I want to do is I want to it's car, isn't it? It's get C is what I want actually. Isn't it? I think it's just standard in. Okay. So basically it's going to wait for me to actually tell it to stop. So hopefully we should see somewhere in here. There's threading. So we've got a priority of 20 here. Priority of 20 still. So did I actually do that correctly? Maybe that's not what it's supposed to be doing actually. We want to use explicit shed. Let's just try that then. Oh, that's interesting. Now got 2. Probably for each of our 2 threads. Yeah, and then one of them goes away when the other one finishes. That's kind of cool. Well, this is it's not exactly working as I was expecting, but I don't think it's necessary. It's too. It's not too important actually. That I suss this out, I guess. Yeah, I guess it's not too important. I'm happy to move on. I think. Yeah. Yeah. I mean, the main thing, I just wanted to reacquaint myself with the attributes that you can set, basically. Yeah, so we've looked through these. Shared policy, set scope. We've thought about that. The set sig mask. I haven't done that, so I'm going to skip this for now. And then set stack address, set stack size. That's just to do with setting obviously the stack for the particular thread. So yeah, I think that's all. Now, there's one thing that I had a look at actually since last stream. You can see here I've got like a load of definitions here. There's a couple of things. There's the definitions, and there's also this LP thread. Now, what I'm going to do, I'm looking at sorry. If you go to this file, sorry, it's not here, is it? pthread create. This is compiling with pthread. So I think I'd read this, but then I typed it, and then I was like, well, hang on. Usually it's like L and then something. So I just typed that in without actually going back and checking what it said. So that works. That's what it says. But I have a feeling this might also work. So you don't actually need to define it. Oh, let's just double check that it does still run. Yeah, it does. So you don't actually need to do that at all. But also there's this use GNU thing. And yeah, why did that was for, I think it was a get affinity. Yeah, it's one of those NP things. Sorry, it was GNU source, wasn't it? So you need to use GNU source. You need to define GNU source in order to get that function. So we're talking about getting a function from in here. Okay, let me just. So this is like if def GNU use GNU, and I was like going through the usual routine that I'll go through when things don't kind of work as I'd expect. It's like going into the H file and seeing what does it use, or what if def is around it. So this has use GNU, so I kind of like used that, right? And then when you do that, you kind of need to pull in a bunch of other things. But the thing that the man page doesn't actually tell you is that this isn't the whole story. I mean, they do say C feature must go macro 7, and I sort of never read that, but I went ahead and read it. And what you're actually supposed to do with this is you're supposed to say define GNU source, and you're supposed to add an actual value. So, define it as 1 or something, and then it'll all work. So, what was it? If you just do this and then kill all of that, it doesn't work. So I'm sure that that's what it was. Now, is this a compile link with pthread, I think, as well then? So define GNU source 1. This is all saying just use GNU source. Defining this macro with any value implicitly defines all of those other things. Honestly, I swear that I did this offline, and it worked. So it's saying implicit declaration of function piece of thingy. Oh, we've got an implicit declaration of function CPU count. Wow. Gosh, so what was it that I actually discovered? Yeah, GNU source isn't even mentioned in here. Ah, hang on, is it GNU source before anything? Is that what it wanted to do? Yeah, that's it. Let me just double check in here. Defines macro with any value, implicitly defines all those things. Yeah. In order to be effective, a feature test macro must be defined before including any header files. So there you have it. So there's two components to this GNU source thing. Well, I suppose when you've got a feature test macro, you need to give it a value, and you need to include it before everything else. Now, do you still need to give it a value though? you don't need to. So all it is you just need to define it before everything else. Blimey. Well. So there we go, we've learned something there. You just declare it before everything else. So I think that's it for the recap. Yeah, I do. That's it for the recap. So now, how long have we been going for? Wow, that's 40 minutes. 40-minute recap. It's been unfortunate it's been this long. But anyway, let's try and go on to other passages new. So I wanted to learn stuff like mutexes today. So we've got these things. We made some notes last time. Mutexes, conditional variables, atomic self-semaphores. Now I might be misunderstanding what all these kind of how they all relate to each other. But I think mutex is a thing that I want to certainly learn. So to start down this path, let's have a look in pthread and just search for mutex. So here we go with mutex related things. Okay, so there's a few things for mutexes. Maybe it might be an idea to just scan through this little section and just see what functions are available to us. And then have a look at the man pages of each, I guess. So we've got mutex init, mutex destroy, mutex try-lock, mutex lock. Yeah, I suppose actually before we actually kind of embark on this, I suppose I should say what I sort of imagine mutexes are supposed to be doing. And I think what they're supposed to be doing is locking bits of memory so that only particular threads can actually operate on that memory. Now that's what I think it's supposed to be doing. But that might well be complete nonsense. And we'll see if that is nonsense as we proceed. So yeah, init, destroy, try, lock and lock. We've got timed lock, clock lock, unlock a mutex, get prio ceiling, priority probably. Yeah, set priority ceiling. Consistent. Declare the state protected by mutex as consistent. And then we've got an NP consistent here. I think NP stands for non-POSIX, by the way. So we've got mutex attributes stuff here. This is going to be similar to the thread creation attributes. Init, attribute destroy. Get the process shared flag of the mutex attribute. So, and then P, and then set P shared. Return in kind, the mutex kind attribute in attr. Set type, get protocol. Set protocol, get priority ceiling. Set priority ceiling, get robust. Get robust is the mutex. And then get robust non-POSIX, set robust, and set robust non-POSIX. Okay, interesting. Well, I suppose let's start at the very beginning and see what the pthread mutex init is all about. So it doesn't seem to have much information about this. So you're supposed to refer to the p3 mutex destroy man page for the description. Mutex and conditional variables. Okay, so the p3 mutex destroy function shall destroy the mutex object referenced by mutex. It's interesting that they have them in that order as well. Destroy and then init. The mutex object becomes in effect uninitialized. An implementation will cause p3 mutex destroy to set the object referenced by mutex to an invalid value. Can be reinitialized. Destroy initialized mutex that is unlocked. Attempted to destroy locked mutex, or a mutex that another thread is attempted to lock, or a mutex that is being used in a pthread content wait, or conwait called by another thread without non-defined behavior. That shall initialize the mutex reference by mutex with attributes specified by attrib. If that's null, the default mutex attributes are used. The effect should be the same as passing the address of a default mutex attributes object. Upon successful initialization, the state of the mutex becomes initialized and unlocked. See section 2.9.9, synchronization object copies and alternative mappings for further requirements. In cases where default mutex attributes are appropriate, this macro can be used to initialize mutexes. The effect should be equivalent to dynamic initialization by call. It's p3 mutex init, which parameter attribute specified as null. Okay. Try locking a mutex. Lock and unlock a mutex. Okay, so you've got try lock and unlock. And you want to refer to lock. Oh my god, wasn't it try lock and unlock? This is probably going to also refer to the unlock. Oh, maybe not. If it's locked by another, the calling thread shall block until the mutex becomes available. Okay. This operation shall return with the mutex object mutex in the locked state, where the calling thread is its owner. Here we go, rationale. Mutex objects are intended to serve as a low-level primitive from which other thread synchronization function can be built. As such, the implementation of mutexes should be as efficient as possible, and this has ramifications on the features available at the interface. The mutex functions and the particular default settings of the mutex attributes have been motivated by the desire to not preclude fast inline implementations of mutex locking and unlocking. Since most attributes only need to be checked when a thread is going to be blocked, the use of attributes does not slow the common mutex locking case. Likewise, while being able to extract the thread ID of the owner of a mutex might be desirable, it would require storing the current thread ID when each mutex is locked, and this can incur unacceptable levels of overhead. Similar arguments apply to the try and lock operation. Okay. So yeah, we've got the idea of initializing, destroying, locking, try locking and unlocking. I suppose the protocol could be handy to look at. Inherit, none, and protect. Okay, I think I could do with probably just trying something out, I guess. Pre-thread mutex 2. I think there needs to be some sort of shared mutexes going on here. Because I think the idea is that, you know, they're supposed to be able to try locking, isn't it? And you're only supposed to be able to unlock it if you are the owner, isn't it? I mean, it sort of actually seems like you're supposed to just initialize your mutexes straight out of the gate. And only destroy them at the end of the whole thing. And it's when you know, like the threads themselves are only supposed to be locking and unlocking. I think that's probably what I would be saying you're supposed to do. So, before we create the threads, let's do this. And then after they've completed, let's destroy them. It's kind of funny. Oh, right, yes. It's because this hasn't quit, A can just continue on, even though we've got detached set. That's kind of funny. Okay, but we've got mutexes 1, 0, and 1 initialized and destroyed, and in thread A stuff, it is going to come in and it's going to lock its mutex. While it does its work. So I think either way it's going to do this. So yeah, if so this should return yay or nay, shouldn't it? So for show the meters or reference meters in the locked state with the calling thread of its owner. It should behave as described in the unlock when not in a column of that. So error returned. So we should get an error. What's the return if it... Here is the relock. Ah, yeah, okay, so I think I'm starting to see what the point of mutexes are. I mean, obviously it's to do with synchronization between threads. But basically, if you want something to happen before another thing, that's when you use mutexes. So let's try and make all of thread A stuff happen before thread B stuff, right? I think if we can do that, then we've basically learned what the point of mutexes is. So we're going to lock. Yeah, so A is going to lock and it knows that it doesn't need to check, right? Yeah, I think I can see this. It doesn't need to check because it is going to be doing the thing anyway. So this is going to lock and then do its work and then unlock. Thread B stuff, meanwhile, is going to be saying, we're going to be talking about the same mutex. And it's like, if unlock, isn't it? Oh no, it's just going to try and unlock, isn't it? Is that right? Because it'll... won't this block? No. Did you say it will try and block? If the mutex is already locked by another thread, the calling thread shall block until the mutex becomes available. So yeah, thread A did its stuff first as well. Ah, hang on. Did I use try unlock? No, I just did unlock. If the mutex is already locked by another thread, the calling thread shall block. Ah. So let's just try that then. Hey. So it should finish, shouldn't it? And then it'll unlock. Yeah. Yeah, that's awesome. Now you can sort of see the pattern here as well. Because these two are doing exactly the same stuff. Lock and then unlock. I mean, just to nail that one down, just make them use the same function. Oh, except for the fact we're not going to be able to see who's doing what. When he goes back down to 4, that's going to be thread B, basically. Yeah. Okay, so that's kind of cool. So here we've got 2 threads that aren't really centrally coordinated. They're kind of coordinating between themselves. So what does try lock do? Except that if the mutex object referenced by mutex is currently locked, the call shall return immediately. Remember the call is for the mutex lock count shall be equal to 1. Mutex try lock function shall immediately return success. So there's a lock count, it seems. Okay, so yeah, I think my understanding of mutexes has developed since the start of the stream. So I was originally thinking that a mutex was like a way to lock a piece of memory so that only a particular thread can touch that memory. But it isn't that at all. It's actually a way to sort of block execution, basically. You use them to ensure that one thread doesn't operate until another thread has finished doing what it wants to do. So you can sort of use this to do the thing of ensuring that you don't have two threads both writing to a database at the same time. Yeah, you could. That would be a usage of that. We also had conditional variables, didn't we? Let's see where they come into the picture. We've got init, destroy, try lock, unlock. And unlock is going to be somewhere down here. So we've got timed lock. Clock lock. Gosh, I completely blanked on what I was actually supposed to be looking up there. Locking and unlocking. Conditional variables. Yeah. So, let's see a version of that. Interesting. All threads waiting for conditional variables. Yeah, so this is going to be a thing where you've got a sort of coordinator thread, isn't it? Yeah, we're doing an hour and 20 minutes. What I'm kind of wondering here is, should I sort of mock up my actual use case for threading? You know, and sort of see if conditional variables factor into that at all. I suppose actually we can just test it out, can't we? We could try it. Just reminds us what he wants. He wants a condition. I suppose here's one for you. There probably isn't a guarantee that thread A operates before thread B. Is there? Right. Oh, maybe there is. Yeah, it kind of seems like it is. But we could have a condition that says that A can only run if B has finished doing its thing. So B doesn't care. B can just get on and do it. Actually, does this actually make a difference? I wonder. Oh, hang on. Could we also say the priority is like -32? No. Well, let's leave them in. Yeah, let's just do this. Oh, I think this was also part of that, wasn't it? So yeah, could we say here we've got an example. Okay, so it's just whatever you want it to be. So we could say the pthread cond t is B is done. Oh, where's not busy? So busy's in int. Is this wait I'm not busy? Ah. Just gonna wait on a condition under mutex. This seemed to be locked before. Yeah, cool. So obviously A won't run because B ain't actually saying that it's finished. But we should be able to say Yeah, I mean, it is just sitting at this point, isn't it? I suppose we could actually just do this. It could be fun to see as well. See it all ping-ponging around. Yeah, so how it would. Ah. So now we hit the log. But it's saying we're stuck on this now. I mean, surely it can't be this, can it? Broadcast and unlock. Interesting. So there was that thing about it assumes that the mutex is locked, didn't it? Oh, sorry, it was conned, wasn't it? It's not what they're calling thread. Okay. Okie dokie. So let's say the mutex locked by the calling thread. So rather than this locking and unlocking, could this be right? It's now waiting for B stuff to happen. And now that it has, it can continue. It's kind of cute that it follows on. That was not planned. Okay, so when using conditional variables, it is the calling thread who initializes it. Right, suggest. And the calling thread itself also locks the mutex, but you can sort of see that I'm not even using that mutex, to be honest with you. So that's kind of moot, isn't it? Because all we're dealing with here is the conditional variable. So yeah, I wonder how I'm supposed to use them in conjunction with each other. Yeah, I think this might be something. This is something to think about, I think. Yeah, after an hour and 42, an hour and 43. Yeah, I think I might call it a day there. I think we've basically done what we sort of set out to do. We've started to learn how to coordinate threads. We've sussed out what mutexes are. How we sussed out how to do conditional variables. So yeah, I suppose just a recap of the mutexes. Let's just do that. So in order to recap the mutexes, I'm just going to take the conditional variables out of the equation, just for the moment. So it's still being initialized, but it's not being used. So yeah, there we have thread A getting on with its stuff, and then thread followed by thread B, and the thread A stuff and the thread B stuff functions are both identical. So you could really have, you know, a couple of threads both using the same function. To do their work. But the thing here is that you're not actually guaranteeing that thread A happens before thread B. I don't think. Yeah, so basically it's going to come in. Both of these functions are going to get kicked off. I could just step through it actually, can't I? So we do these two things. So there we created a thread, so that should actually be starting to do some work now, I think. Yeah, so you can see that thread A stuff is already printed out 8 and 9. Before we even got to creating this one. And then this is going to block on these two functions. So that's blocked on that. Now B needs to continue. try and step in there. Oh, of course, we could have got A finishing before B because of the mutexes. Yeah, and thread A is returned. Yeah, we're not quite getting the whole ping-ponging about experience. But yeah, needless to say, we've got these mutexes set up, really using one of them. And we're essentially getting thread A, locking it, before thread B starts. So thread A, it's locked it. When thread B comes to here, it's blocking on this mutex because it's locked. Thread A then proceeds to do its stuff, and at this point, once it unlocks, that enables B to progress past here, and it does its work. So that's basically how mutexes are working here. And then the other thing that we did was the conditional things. So in this way around, we don't lock and unlock in there. And in fact, we don't really need to lock out here either, I don't think. In this way, because we've only got A waiting on that condition, we're basically saying that this waits until B is finished. B doesn't bother to wait for that. B comes in and broadcast. Can I actually do signal, by the way? Yeah, I can also do signal. So this will, obviously signal that it's finished. And then once it's signaled that it's finished, this thread can then proceed past this wait. So they're sort of doing similar things. The mutexes and the conditional variable. Except, I suppose, well, what would it be? Would it be that you've got more control over the order of things when you're using the conditional variable? I mean, that's what's kind of happening for me here. I'm able to say that thread B is supposed to happen before thread A, and that thread B doesn't need to care about the B has finished thing. It doesn't need to wait for it because it is the thing that is needs to finish. Yeah, maybe that's kind of the difference. But anyway, yeah, I think these are things to mull over. And then next time I think he's going to be mocking up the sort of setup that I need, I guess. going to be mocking up the actual whole thing. I'll just finish by showing that again. So yeah, once again there's cinema running. Here is ref still running, and then here is the test thing running. So yeah, the idea behind this alternating thing is to try and unify all of these things so that they're all in the one program, basically. And it's this sort of thing that I'm going to be mocking up. So for this, we're going to be having a thread that is waiting for file system events to happen. With this one, I'm not sure what this is going to be waiting for. It's going to be sort of waiting for instructions to arrive, I suppose. And this one here is going to be waiting for user input. So yeah, I think that is what is going to be happening next time. I'm going to be mocking up this sort of thing, just to see how they sort of interact with each other, I guess, and how we can get them to synchronize or whatnot. So yeah, thank you very much for watching, and yeah, I guess I will. I guess I'll be here for the next one, won't I? So yeah, that's it. Until next time. Laters.